Welcome back, everybody. This is our first video in NEET previous year question series for chapter Dual Nature of Matter and Radiation of class 12th. Before this video, we have made several videos in this series and all of those are available on our channel's playlist section. We have also started similar series for JEE previous years. So if some of your friends are preparing for JEE, then you can guide them through those videos and you can yourself can get some additional practice from those questions. And if you find these videos useful, helpful, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us, then do uh, we can say subscribe to our channel. And if you want to support us financially, you can scan these QR codes in front of your screen and help us with some donations. With this, let's start today's video. In the first one, in a discharge tube, ionization of an enclosed gas is produced due to the collisions between neutral gas atoms, positive ions, negative electron and neutral atoms, and photons and neutral atoms molecules. So we know that in a discharge tube, what happens that electrons are accelerated in a discharge. Let me adjust thickness slightly. So electrons are accelerated, and when these accelerated electrons strikes neutral gas atoms, then there is what happens? There is transfer of energy. And due to that, what will happen? There will be ionization. So that is the reason of the question as asked. So that is option C, that negative electrons and neutral atom molecules, they collide with each other, and due to that there is we can say ionization happening of the enclosed gas. And here you have to keep in mind that only ionization is happening, not excitation, because in case of ionization, quantization is not necessary, but for excitation, quantization is necessary. Now moving ahead, J.J. Thomson cathode ray experiment demonstrated that cathode rays are stream of negatively charged ions. All the masses of atoms is essentially in the nucleus. The E by m of electrons is much greater than the E by m of the proton. EM ratio of cathode ray particle changes with different gas placed in the discharge tube. So here we know that right answer will be option C, as mass of electron is less as compared to mass of proton. So E by m for electron will be greater as compared to E by m for the proton. Moving ahead, which of the following is not a property of cathode rays? So the property will be that it does not deflect in electric field, because cathode rays carries charge, so they will be deflected, accelerated or decelerated in electric field. So option B is not a property of the cathode rays here. Now moving ahead, a source of light is placed at a distance 50 centimeter from the photocells and stopping potential found to be V naught. If the distance between the light source and the photocell is made 25 centimeter, the new stopping potential will be. So we know from the photoelectric effect experiment that the stopping potential, we have a relation that E times Vs, where Vs is the stopping potential, is equal to energy of the photon minus work function. And this can also written as that kinetic energy maximum of electron is equal to E minus phi. And from these two, if we combine, then we will get EVS is equal to KE max. From all these things or all these three relations, we can easily find out, and also we can write that E is equal to H nu, where nu is the frequency. That in none of the given formulas there is some relation of the stopping potential with the distance. So basically we can say Vs is independent of stopping potential. Sorry, distance. Independent of distance. And if Vs is independent of distance, means stopping potential will not change. That is option B for us. Let us move ahead. In a photoelectric emission process from a metal of work function 1.8 electron volt, kinetic energy of most energetic electron is 0.5 electron volt. The corresponding stopping potential is. So here we know, as already discussed in the previous question, uh, that maximum kinetic energy is equal to E times the stopping potential, and here maximum kinetic energy is 0.5 electron volt is equal to E times Vs. So E gets cancelled and stopping potential is 0.5 volts. That is option B for us. Let us move ahead to the next one. Photoelectric emission occurs only when incident light has a more than certain minimum frequency, because it has to be more than certain energy, and that energy depends upon frequency, not on the power, only on the frequency. So option C is going to be the right answer here. For the next one, when a monochromatic radiation of intensity I falls on a metal surface, the number of photoelectrons and their maximum kinetic energy are N and T respectively. If intensity of radiation is 2I, the number of emitted electron and their maximum kinetic energy is. So we know that maximum kinetic energy Ke max is given by this relation, that it is equal to H times nu, where this is the frequency of the incident radiation, minus phi, where phi is the work function. So maximum kinetic energy does not depend upon intensity, whether it is I, 2I or 3I. So it does not depend upon the intensity. So maximum kinetic energy going to stay same. And from that we can say option A is wrong and option C is wrong. Now we also have to calculate the number of emitted electron. Now, number of emitted electron, let's say n is equal to power, where P is the power of the incident radiation divided by the energy of the single photon. And we also know that intensity is basically power by area. So from this we can write that power is equal to A times I. So here number of electrons will be AI by E, or number of electron is directly proportional to intensity I. So if I in gets doubled, if I gets doubled, then number of electrons and number of photons will also get doubled. So initially it was n, now it will becomes 2n. So 2n nt, that is option B as the right answer for us. Let us move ahead to the next one. The potential difference that must be applied to stop a fastest electron emitted by a nickel surface having work function 5.1 electron volt when ultraviolet light of 200 nanometer falls on it must be. Now we know that stopping potential EVS will be equal to energy minus work function. Now work function is in electron volt here, so we have to find out energy of this light, UV light, in electron volt. So for that we can use that E is equal to Hc by lambda, that is the relation, and that can be written as 1240 electron volt nanometer. That is the value of Hc in electron volt nanometer divided by lambda, that is 200 nanometer. So 200 nanometer gets cancelled, 0 gets cancelled, and this is comes uh, 62 by 10. So that is basically 6.2 electron volt. So now we can write that EVS is equal to 6.2 electron volt, that is energy of incident radiation minus work function, that is 5.01 electron volt, and this will give us around 1.19 electron volt is equal to EVS. E gets cancelled and our stopping potential is 1.19 electron volt. That is option D for us, 1.2 1.2 volt. So, oh, sorry, electron volt, not electron volt, it will be volt. Moving ahead, the figure shows plot of photocurrent versus anode potential for a photosensitive surface for three different radiation. Which of the following is a correct statement? So, as per the diagram, let me zoom it out slightly. Yeah, I think no, it will be better. So here we have photocurrent, and here we have anode potential, and here we have retarding potential. So if we observe the graph carefully, we can note here that here we have three curves, curve A, B and C. For curve A and B, we have same retarding potential, or we can say same stopping potential. And for curve B and C, we have same photocurrent. Current. Now coming to the stopping potential, we know that stopping potential only depends upon energy of incident radiation. So it means A and B will have the same energy and same frequency. So this our conclusion is A and B have same energy slash frequency. Now coming to the second one, that same photocurrent. So that photocurrent depends upon intensity, or basically number of photons per second. It does not depends upon frequency, although there is cutoff frequency below which there will be no current. But after cutoff frequency, it only depends upon intensity or number of photons or photoelectrons. So from this we can write that B and C will have same intensity, as they have the same photoelectric current. So in the first one, in option A and B represents incident radiation of different frequencies, so it is wrong. B, curve A and B represent incident radiation same frequency but different intensity. Yeah, B is right here, because current for A and B is different. Now C, curve B and C represent incident radiation of different frequency. B and C, different frequency is given and different intensity. So regarding frequency, as B and C have different retarding or different stopping potential, so surely their frequency is different, but they have the same intensity, and it is mentioned to be different intensity in option C. So C is wrong. Now D, curve B and C represents incident radiation of same frequency. That is also wrong. So only option B is right here. Let us move ahead. The number of photoelectrons emitted for light of a frequency mu higher than the threshold frequency mu node is proportional to. So we already discussed that number of photoelectrons is proportional to intensity of the radiation. So that is option C here. Let us move ahead. A 5-watt source emits monochromatic light of wavelength 5000 angstrom. When placed 0.5 meter away, the liberated photoelectrons from photosensitive metallic surface. When the source is moved to distance 1 meter, the number of photoelectrons liberated will be reduced by the factor. So here we have power 5 watt and wavelength is 5000 angstrom, and it is placed 0.5 meter away. So we know basically that intensity that is reaching is equal to power by area, and here area will be 4 pi r square, because we consider that radiation is emitted along the sphere from the source. So this is the intensity which is reaching to the our photosensitive metallic surface, and basically it has to be multiplied by area of the surface also. That will represent the energy received by the surface. But we will go with this formula. From this we can write that I is proportional to 1 by r square. So I1 divided by I2. I1 is the intensity at 0.5 meter and I2 is the intensity at 1 meter. That will be equal to 0.5 square, and here we have 1 square, and this will give us 4. So basically we can say I2 is equal to I1 by 4. Now we know that number of photoelectrons directly proportional to intensity. So if intensity reduces by a factor of 4, then the photoelectrons will also reduce by the factor of 4. So option D will be the right answer here. Next one. A photocell employs photoelectric effect to convert. Now, if we see here in the given options that change in frequency of light into change in electric current, change in frequency of light into change in electric voltage, change in intensity of illumination into change in photoelectric current, change in intensity of illumination into change in work function of the photocathode. So basically work function does not meet our criteria, so option D is wrong here. Now there can be some doubt regarding that whether it is converting change in frequency or change in illumination. So if we cover the basic, that sun spectrum is given by this short code that we give, and frequency for each color is constant. Frequency for each color or each radiation is constant, but what happens that intensity of light changes. How it changes? At sorry, not at, as earth rotates, then what happens that sunlight falls normally on surface. So due to earth rotation, the tilt or the angle on which sunlight is falling on the earth surface, that changes, and due to that angle change, intensity received by the surface changes, and that change in intensity gets converted into photoelectric current. So option C is going to be the right answer here. So with this, let's move to the next one. In the question number 13, a photocell is illuminated by a point source of light 1 meter away. When the source is shifted to 2 meter, then we have to find out that which of the given option is right here. In the first one, each emitted electrons carries 1/4 of the initial energy. Second, number of electrons emitted is half of the initial number. C. Each emitted electrons carry half of the initial energy, and number of electrons emitted is a quarter of the initial number. So in the first one here, in the option A, it is discussed regarding energy, and in the, we can say, option C also, it is discussed regarding energy. That in the option A, it is 1/4 of the initial energy, and in option C, it is one half of the initial energy. Now, for photoelectric experiment, we know that kinetic energy maximum is equal to h nu, where h nu is the energy of the incident photon minus the work function. So this maximum kinetic energy does not depend upon the distance. Whether the distance is 1 meter or the 2 meter from the source, it does not change. It stays the same, assuming that there is no air between the plates, so that there is no collision happening between the electrons and air. So they are not losing kinetic energy due to resistance of air, and that is the basic assumption, and that is we can say practically not true, but in theory that is always the condition which we assume by default. So as there is no air, so kinetic energy will not change. So we can say option A and C both are rejected. Now coming to B and D, that number of electron emitted. So now we know that number of electron depends upon, let's say that is Ne. Ne represents number of electron. It depends upon number of photon incident on the surface of plate, and number of photons Np is basically equal to power by energy. That is the number of photon emitted. This is number of photon emitted, not actually number of photons that are being get we can say that are striking uh, on the metal surface. For that, let's explain it this how. That suppose this is our source. This source has power P, and energy of the photon it emits is equal to E. So the number of photons per second it is emitting, that is P by E. Now here this is our plate. This is our target plate. So that photon will go like this. Now these photons, these NP will go in all directions. They will move in all directions. So they will be distributed over area. What area? 4 pi r square. Suppose this distance is capital R. So the number of photons per unit area will be equal to Np divided by 4 pi r square. And now number of photons that are reaching here on this plate. Suppose this plate has a side A and width also. Suppose this is a square plate. So the area, the number of photons that are reaching on the plate, that is, let's say NPL, that will be the number of photons per unit area multiply the area of the plate, that is A square. So assuming plate area does not change, Np is not changing because it is power by energy of the photon, both are constant. So basically number of photons reaching to the plate depends upon 1 by r square, where r is the distance of the between the source and the plate. And as distance gets doubled from 1 to 2, it gets doubled, so the number of photon will reduce to 1 by 4, that is 1 by 2 square. So quarter of the initial number, that is option D here. So option D is the right answer. uh, with this, let's move to the next one. When intensity of incident light increases. Now what is intensity? We know that number of photons is power by energy of the photon, and power is intensity by area. So basically from this we can write that intensity is power is intensity by area. Let us substitute it here, that Np is equal to IEA, and from this we can write that Np is proportional to I. So if intensity of incident light increases, here I is increasing, that number of photon will increase, and if number of photons are increasing, that number of electron will also increase. Now number of electrons are increasing, and this is basically our calculation are per unit second. So if Ne is increasing, means current, let's say current, yes, current will also increase. So that is photocurrent increases. That is option A for us. Let us move ahead. The cathode of a photoelectric cell is changed such that the work function changes from W1 to W2, where W2 is greater than W1. If current before and after changing are I1 and I2, all the condition remaining unchanged, assuming the we can say energy of the incident radiation is greater than the work function. So we have to find out condition for the current. Now basically we know that current is, or we can say photocurrent, it is directly proportional to intensity, but it does not depend upon energy of incident photon. Although it is necessary to have energy of the photon to be greater than the work function, but after it crosses work function, then photocurrent is independent of the energy of the photon, and it only depends upon the intensity. And basically intensity is basically np, where np is the number of photons per unit time. So whether we change the material, and provided that the energy of the incident photon is greater than the work function, photocurrent will stay the same. That is option A, I1 is equal to I2. The next one, the threshold frequency for photoelectric effect on sodium correspond to this wavelength, the work function we have to find out. So we know that energy is equal to Hc by lambda, and this can be written as that energy is equal to Hc is 1240 electron volt nanometer, and lambda is here 5000 angstrom. So that is basically 5000 into 10 raised to power minus 10 meter, and this can be written as 500 into 10 raised to power minus 9 meter, and that is 500 nanometer. So we can divide it by 500 nanometer. Nanometer gets cancelled, this 0 gets cancelled, and this will be 2. If we cancel it on 5, suppose this is 125 approximately, so this will be 25 by 10 electron volt approximately, and that will be basically 2.5 electron volt. Now answer is in joule, so that can be converted, that 2.5 into 1.6 into 10 raised to power minus 19. So option B is directly rejected, because here we don't have 10 raised to power minus 19 power. Now 25 and 16, this will give us 0, 1, 5, and this will be 25, so 0, 0, 3, 4. So this will be 400, and here we will have divided by 100 into 10 raised to power minus 19, so approximately 4 into 10 raised to power minus 19 joule. That is option A for us. Now let us move ahead to the next one. If phi is the work function of a photosensitive material in electron volt, and light of the wavelength of numerical value lambda is equal to Hc by E meter is incident on the energy above its threshold value at the instant, then maximum kinetic energy photoelectron emitted by at that instant. So we know that maximum kinetic energy Ke max is equal to energy of the photon minus the work function. Now energy of the photon will be equal to Hc by lambda, and that will be equal to Hc by lambda value is Hc by E. So Hc gets cancelled, and this is basically equal to E. So this becomes E minus phi, and that is option C for us. Moving to the next one. The work function of cesium, potassium, and sodium are given respectively if incident electromagnetic radiation has an incident energy of 2.2 electron volt, which of the photosensitive material may emit photoelectrons. So we know that for electron emission, the condition is that energy of incident photon must be greater than the work function, and here energy of the incident photon is 2.2 electron volt. So it is greater than for the cesium and less than for potassium and sodium. So only possibility for electron emission is for cesium only, and that is option C for us. Let's move to the next one. When two monochromatic light of frequency V mu and mu by 2 incident on a photoelectric metal, their stopping potential become Vs by 2 and Vs respectively. The threshold frequency for this metal is. So we know that relation for stopping potential is basically E times Vs is equal to H nu minus work function. So initially frequency is V and stopping potential is Vs by 2. So what we can write here, we can write that E Vs by 2 is equal to H nu minus phi. For the second case, frequency is nu by 2 and stopping potential is V. So for that we will have EVS is equal to H nu by 2 minus of phi. Now what we can do here, we can divide both of these equations, this and this. So what we will get, basically half is equal to H nu minus phi divided by H nu by 2 minus phi. Cross multiplying we will get H nu by 2 minus phi is equal to 2 H nu minus of 2 phi, and from this we will get a minus phi plus 2 phi is equal to 2 H nu minus H nu by 2. This will provide us phi, and this will provide us 3 by 2 H nu, and this can be written as H times 3 by 2 of nu. So phi is equal to H times the frequency. So stopping frequency, or the we can say threshold frequency, will be 3 by 2 nu, and that is option D for us. Now let us do one more. So we will cover up to 20 questions in this video. The work function of a photosensitive material is 4 electron volt, the longest wavelength of light that can cause photoelectric emission of the substance approximately. So that can be calculated easily, that E is equal to Hc by lambda, and from that lambda is Hc by E, and that will be 1240 electron volt nanometer divided by 4 electron volt. Electron volt gets cancelled, and this will give us 310 nanometer. That is option D for us. So with this, we end this video here. Hopefully what we have discussed here is helpful to you. If you have any doubts or suggestion, you can put them in comment section. I will try to resolve them. And if you find these videos helpful, then do press like button, share these videos, subscribe to our channel. If you want to donate us something, scan these QR codes. With this, again, thanks for watching, and we will meet in next video.